Okay, so one last bit of, this old guy waxing poetic. I think let's just take the words from Bill and Ted and just be excellent to each other. The attendance code is up. It's 8377. Okay, so on Friday we talked about homogeneous nucleation, and we said that even though this never really happens in real materials, it's a really important theoretical understanding. And I want to just take 5 seconds and go over this figure again, because this is one of the most important figures from this class, right? And it's really encaptures so many really fundamental physical concepts, right? That without an undercooling, we don't have any driving force for nucleation, right? And the reason for that is because we have an energy penalty that we need to pay to overcome the interfacial energy, right? We have to create new surface when we make an interface. And we remember from the Gibbs-Thompson effect that we're going to have a chemical potential. We have the system with the interface is going to have a higher Gibbs free energy than that without, and that the penalty that we have to pay per unit volume, right, is greater when we have a smaller, right, per volume of our secondary phase is proportionally greater the smaller the radius, because the surface area to volume ratio is higher, right? So we have a penalty that we have to pay that goes with the radius squared, but we get the benefit because we want to be at our thermodynamically stable phase. That's something that's proportional to r cubed times the change in temperature. So when we have this first term that that's initially larger, the interfacial energy term, but the volume free energy term grows faster. So that means we get a maxima and then a decrease. And any nuclei that have a radii smaller than this maximum here, they're just going to dissolve back away. Any nuclei that are larger are going to grow, right? And so we can think of this hump here as the activation energy that we have to overcome to nucleate, right? And this drives so many things. This is really, really important in solid phase transformation, right? In that case, we also have an additional term, that's the elastic strain term, that needs to be considered. But the same concept holds, right? And then we looked at what goes in here, and we realized that the surface energy cube in the activation energy, right? So that means that we really want to, for heterogeneous nucleation, we really want to see what we can do about lowering this interfacial energy term. We took a look at Boltzmann statistics, and we realized that from the exponential dependence is that we really have no clusters smaller or larger than the maximum one predicted, right? And so that means that our nucleation rate is essentially going to look like a step function. So we've got a critical undercooling that's defined by where the maximum expected cluster size in our system is equal to R star, right? And that happens at about 78 kT. Undercooling of minus 78 kT. And that's where we wrapped up Friday. I want to spend a little bit of time on a set of really beautiful experiments was done by David Turnbull. David Turnbull was a scientist who worked for General Electric in the 1940s and 1950s. He died in the 1990s, early 1990s, if I remember correctly. But anyway, he was one of these people who did so much beautiful work in the research and development lab of the General Electric Corporation. Another famous person that came out of that same lab was John Kahn at the same time, who developed the theory for spinodal decomposition. And when we do diffusion, we'll talk about the Kahn-Hilliard equation in some detail. So at the time, Schenectady, New York was a powerhouse of solid state physics due to the General Electric Research and Development Lab that was there. But David Turnbull was familiar with the theory of homogeneous nucleation, and he was looking at ways of exploring whether it was true, and if it was true, how can he measure the interfacial energy? And what he realized is that in large systems, whenever you have a large amount of metal, you always have impurities that gives you heterogeneous nucleation. So David Turnbull, he set up a large number of very small systems, little tiny droplets of metal. And his assumption was that if I have many more droplets than the number of expected impurities, that means most of the droplets are going to be free from impurities that can catalyze the freezing, in his words, heterogeneously. And so those are going to freeze out right away, while the rest of the droplets will nucleate homogeneously. And I can measure the maximal undercooling that we get, and from that, calculate the interfacial energy. And this experiment was really beautiful. There was a guy, Robert Check, who designed some of the experimental apparatus with him. And this was done with a optical microscope, right? This was done at roughly at around the same time as the invention of the transmission electron microscope. So these were all done optically. There was definitely not the provision to be able to do these kind of complicated in situ experiments in the TEM. So what he did was this is the objective for the optical microscope, small amounts of metal particles on a quartz window, and this is under either under vacuum or an inert gas. There's a heater and a little thermocouple here. And so the heater can be turned on to melt these little droplets, right? And remember, from the Gibbs-Thompson relationship, we know that these metal droplets are going to melt at a temperature lower than the equilibrium melting temperature. And then shut the heater off, recorded the temperature, and figured out when everything is going to freeze, right? And so here we see gold particles at 1070 C that are molten, and then these same gold particles as they freeze at 830, right? And you can see a visible difference when the particle goes from liquid to solid, right? And what's interesting, I think, is just a little aside, is, this is not sort of considered good practice anymore, right? he lists an absolute magnification, right? Of course, now this is at a different magnification on your screen and in your notes than it was published in the journal, right? So we really don't know what the physical size of these are unless we manage to get a paper copy of the journal. But anyway, these are small, right? Obviously larger than the diffraction limit for for light, right? But still very small droplets, right? Much smaller than a millimeter. Right, nowadays the right way to do this would be to actually put a micron scale bar on the image so that we know what size things are even as we do that. But back in those days, everything was done on all microscope images was of course done on film, and you had a standard size for microscope film. So when you developed the prints, they were all a standard size viewing window, unlike a digital image that can be sort of any size. So if you put 75x here, you could figure out what everything was. And the really nice thing about this is you can see the amount of undercooling that he had. So here's the actual melting temp, right? And the undercoolings that he observed. And you can notice that for a lot of these, he was able to get very sizable undercoolings, a couple hundred degrees C or K, right? Which tells you that the interfacial energy in creating a solid from a liquid in these metals is fairly significant, right? Right. So we can see here the these interfacial energies, right? Of course, not CSI units, right? They're in units of ergs per centimeter squared, right? So you have to convert that to joules per meter, right? But you can see the sizable energy penalties that you have. And of course, the question was, are these accurate, right? Should the undercooling actually be larger, and it's just because you're still nucleating heterogeneously from some other source? And so the theory says that the we didn't talk about it, but the solid state physics says that the surface interfacial energy should be proportional to the heat of fusion of the material. And you can see that for the different crystal structures, you do get that, with aluminum being a little bit of an outlier. So what this seems to suggest is that the interfacial energy for aluminum, as reported on this table, is probably a little under what it should be. But anyway, it's just, these are a really beautiful set of experiments. I'm asking you to read the papers for Friday, right? They're 2 short papers, and people just don't write scientific papers like this anymore. I mean, this was dozens of really complicated experiments, all compared in one short paper, right? And nowadays, science has, there's such a pressure to publish a larger number of papers, right? This probably would have been broken up into, a publication per each of these metals, with maybe a little bit more experimental and analysis details. But these are just really, really classic scientific works. Okay, so that was homogeneous nucleation. Like we said, most things, it's very rare to actually get, where's my outline? And why does it say 1 out of 100 slides? Okay. LaTeX went screwy. Okay. Well, anyway, it's very rare to get homogeneous nucleation. Most of the time, we have heterogeneous nucleation. Right? And so, as I said before, if we look at the nucleation for the activation energy for nucleation, we see we have this interfacial energy to the cube, right? Nothing else in here we can change. We can't change the melting temperature of our material. We can't change the latent heat of fusion. We're at a particular undercooling. So the only thing that we can affect in our system is to reduce the interfacial energy, right? And the whole idea behind heterogeneous nucleation, instead of forming a nuclei completely in the liquid, we form a nuclei on something, right? Where the cost to nucleate on this something is less than the cost to nucleate homogeneously, right? And so we have to take a tiny little detour into interfaces. So we have a slight
Question before we move on.
Yeah.
The L, that's the latent energy. Is that related to the interfacial energy or more to the temperature?
So, so from the experiments, right? I just showed that this latent heat is proportional to the solid liquid interfacial energy linearly.
Okay, they use different symbols.
Right, it is, but it's the same latent heat. It's just different symbols from the Turnbull paper. Right? So these, you could potentially simplify this a little bit more, knowing that these have a strong correlation, right? You can make an approximation. But in general, I think it's good to keep it because these are different phenomena, right? They just sort of have a same controlling, different parameters, but they have a same sort of controlling physics, right? So what we have to remember about interfaces is, right, interfaces have tension, right? It's like a string or a rubber band pulled tight, right? The interfacial tension is what keeps a soap bubble round, right? And we know from our discussion of Gibbs-Thompson, right, that this interfacial tension can affect the chemical potential. It affects the free energy of our system, right? And we know that the higher the interfacial energy, the higher this tension is going to be, right? So if we look at this image, this is an austenitic stainless steel, right? And I see a lot of different types of grain boundaries, right? So here we see, right here, we see two sort of standard grain boundaries, right? And we can tell just by looking at these that these are general sort of high angle grain boundaries. There's nothing special about that, right? How can I say that these are sort of standard grain boundaries? Anyone have any sort of idea? No apparent cracking. That's definitely true. But I'm just talking about these interfaces in and of themselves, right? And so, well, I know I have a triple junction here that the angles are about 120 degrees each, right? And so that means the tension of these three grain boundaries is about the same, and we'll see why in a little bit, right? I do know here we have annealing twins, right? And annealing twins, for those some of you might not know, but these are very special crystallographic relationships where you have a mirror symmetry, right? These twin boundaries correspond to a 60-degree rotation about the 111 plane, crystallographic plane in these, or the 111 crystallographic direction. And so you end up with a mirror symmetry, and this corresponds to an error in stacking sequence, right? So FCC usually goes A, B, C, A, B, C, right? In the annealing twin, we go A, B, C, B, A, B, C, right? So we have a error here, but I can categorically tell that this is a lower energy interface than these general grain boundary interfaces. How do we know that?
I'm going to take a shot here because I'm kind of famous for doing that.
Oh,
And
go ahead, take a shot.
I think it's because these grain boundaries look very ordered. There's not a ton of branching. There aren't that many of them. I think there'd be less tension because of that. Am I correct?
Sort of, right? But let me, since I know you're comfortable taking a stab at things, let me ask you sort of a leading question, right? And what does it look like where the twin intersects a regular grain boundary compared to where this grain boundary intersects another grain boundary here?
It's very solid. It appears to be almost seamless
It's
compared to that.
it's straight, right? Right.
Yes.
So this twin is not pulling down. It's not exerting a large amount of tension on this interface. It's perpendicular. That's right. So the intersection angle isn't 120 degrees. It's closer to 90 degrees. Right? So think of these internal interfaces just like soap bubbles, but they're these grain boundaries and interfaces in ceramics and polymers. Think of them as soap bubbles that happen where the motion of them happens on a vastly slower time scale, right? If these were soap films of equal tension, we would expect this grain to bulge down like this, and these three to meet at 120 degrees, but they don't, right? So this is a much lower interface than this one, because this grain boundary can stay straight. So let's sort of formalize this a little bit, right? If we have three ropes and we pull on them with equal tension, right, we're going to have 120 degree separation between them, right? This is just balance of forces and balance of moments, right? Of course, right, all the forces are going straight through this rotational point, right? If we consider this triple point to be our axis of rotation. So that means that we have no net moment, right? But we do have to keep our balance of forces here, right? And if these three forces are equal, these three angles are going to be equal, right? If these forces are not equal, we're going to have, and we're still in equilibrium, right? We're going to have different angles, right? Because what we need to do is balance the vertical and the horizontal component, right? So in this, which interface has the higher energy?
Surface angle 2-3.
Yeah, so the interfacial energy of gamma 2-3 is higher than 1-2 and 1-3, right? It's exerting more tension, and theta 1 is smaller than theta 2 and theta 3, right? But for equilibrium to hold, this relationship is true, right? So we can, think about it. We're not going to sort of discuss it, but think about why this is an unstable configuration, right? Why would this relationship be preferable to this? Why would the system, from an energetic point of view, move to something like this, right? And so here, obviously, right? So if you just work through the condition, you'll see, right? It's just a fun little thing to play with. Not really germane to the discussion at hand for this course, but I thought I'd just throw that out there. So what about boundaries between phases, right? So this equilibrium still holds, right? So we still have the same relationship. We can look at this dihedral angle, right? And what we can look at is we can relate the dihedral angle to the ratio between surface energies, right? And so we can see that if our dihedral angle is exactly 120, our ratio is 1. Okay, so that makes sense, right? As our ratio gets smaller, so sigma 1, 2 is smaller than 1, 1, our angle, as we approach half, our dihedral angle gets smaller. And at exactly 1/2, our angle falls to 0, and static equilibrium is no longer possible, right? So it is really possible to have a very low interfacial energy. So what happens when our ratio is really small? Well, the one phase wets the other, right? So if we have a really low interfacial energy, a liquid phase will completely cover the solid, right? So, you have water that sheets on your car rather than forms nice beads like it would on a waxed hood, right? You get a layer that is completely absorbed onto the surface, right? So the second phase tends to form a continuous film. This is really important in materials because if I have a very low interfacial energy, the second phase can completely wet a grain boundary in a solid or ceramic, even at very low concentrations, right? Bismuth in copper is the example of that. Concentrations of 0.05%, so 5/100ths of 1%, or concentrations of 10 to the -4 can cause severe embrittlement because the bismuth will completely wet the grain boundaries and your copper polycrystal will just fall apart, right? And in fact, that was how they did the first 3D grain size studies, right? So there's a whole field of science called stereology, where you're trying to get at what are the 3D properties of a micrograph of a material, if you're only looking at 2D micrographs. And so there's all these mathematical relationships, and to validate those relationships, people wanted to understand, what do the 3D structure of grains look like? So they made these essentially dissolved, put copper in bismuth, let it diffuse into the grain boundaries, and then it just fell apart and you had individual grain. So then what they did is they took little tiny tweezers and put the grains under the microscope and took 3D pictures of each grain individually and compared this 3D statistics to what was predicted from the 2D analysis, right? So when the interfacial, when this interfacial surface energy is high, the second phase forms discrete particles, right? And they form these clusters at grain boundaries. So grain boundary precipitates are really important for metal. Most of your damaging precipitate structures that you encounter during welding have to do with the formation of grain boundary particles, and right, these can be really powerful strengtheners though, depending, right? It's one hand giveth, one hand taketh away. But why don't these grow to be larger particles? Why do we have why do we tend to have these small discrete ones, right? And again, that's something else I sort of want you to think about. It's not germane to the discussion today, but we'll come back to this when we talk about solid state phase transformations and heterogeneous nucleation of solid state phase transformations, right? But just keep it in your mind. Why don't we just get one big cluster, one big chunk? After all, we would minimize the surface to volume by doing that, right? So for a given amount of this, whatever the secondary phase is, if we made one big spherical chunk of it, we would minimize its surface area. Okay, so what about solid phase vapor interfaces and solid liquid interfaces, right? Well, we still have to hold that equilibrium, right? We still need to, if we know that a solid interface exhibits a tension, it has to be pulling against something, right? So if a grain boundary intersects a surface, what's it pulling against? Well, it's because the gas solid interface also has a tension, right? And what happens is over time we get, the material actually gets pulled in by the interfacial tension, right? This is how we measure grain boundary energies experimentally, right? So what you get is, if you start with this nice polished surface and a grain boundary that's striking the surface, we actually get diffusion, diffusion along the surface to make these little hills, right? And we have this angle that forms, and from this, if we measure the dihedral angles, and we know what this top interfacial energy is, which we can measure by ellipsometry, right? We know the surface tension of water in air, and we know if we put a drop of water on here, we know we can measure the dihedral angle between the water and the metal. And since we know the interfacial energy between water and air, we can, from that, we can calculate what the interfacial energy between the metal and air is. And then if we know this interfacial energy and we look at the dihedral angles, we can measure this grain boundary interfacial energy. So it's a convoluted, difficult experimental process. So yeah, this happens over time, right? So if you polish this metal surface, right, you don't see these grain boundaries in the microscope until you do some kind of etching, right? Right. You've all done that in the sophomore lab, right? You had to polish samples at some point, right? But if you let this sit for a long enough period of time, you would get this grooving effect, right? So it has to happen at a time scale of diffusion in the metals, right? But it's not bulk diffusion, it's surface diffusion. So it's a little bit faster, but still square root dt. So this takes a long time to happen, right? And the amount here, right, this roughness is not something that you can see or feel with the naked eye, right? You need a microscope for this, right? So that's a little sort of divergence on interfaces, because I think some of what we talk about here doesn't make a lot of sense unless we have some understanding of what's going on with the interfaces. So if we go back to our picture of the solid nucleating from a liquid on some third surface, in this case, from the example from the reading, is a mold wall in a casting, because it's talking about the readings, talking about solidification in metals. But our balance of forces still has to hold, right? So if we consider the balance of forces at this point, right, we can think about this as a free body diagram. So the surface energy of the liquid mold or the liquid substrate interface has to equal the surface energy of our solid substrate or solid mold plus the surface energy of the solid liquid cosine theta, right? And so from this, we can calculate what our dihedral angle should be if we know these surface energy terms, right? And if we think about what the formation, the change in Gibbs free energy of making a system like this, right? Essentially what we have is we have our bulk free energy, our volumetric term, right? Plus what are we creating? We're creating this amount of solid liquid interface, right? So it's the area of this solid interface times this interfacial energy. We're creating this solid substrate or solid mold interface, and we're taking away the same size area of liquid substrate interface, right? So our Gibbs free energy change has to look like this expression right here, right? And for homework, it's pretty easy to show that what you get is equal to the same as what we got from homogeneous nucleation theory times a shape factor, right? And this shape factor, if we're going to nucleate, if this is going to nucleate heterogeneously, it has to mean that this interfacial energy has to be less than this, right? Otherwise, we just nucleate homogeneously, right? So our solid mold interfacial energy is less than our solid liquid.
I have a quick question about that equation on the next phase, on the next page.
Yeah.
This is assuming that the nuclei are all going to nucleate in the spherical form, correct?
Yes. Right. So that is true for everything that we're talking about. Non-spherical nuclei changes this, but it doesn't change the physical picture. Right? It changes these volume and surface area terms. Right? But conceptually, the picture is exactly the same. Right? And in a sense, this is a model anyway, because does it really make sense to talk about a cluster of a couple hundred atoms being a sphere. No, it really doesn't. Right? But this is a really good model that seems to work really well. Right? And so you can see now why we spent so much time talking about homogeneous nucleation when the system doesn't actually nucleate homogeneously, when we almost always have heterogeneous nucleation, right? And the fact is, it doesn't actually change what our R star is. It doesn't change our critical radii for nucleation, right? But it does reduce our activation energy by this S naught factor, the shape factor, right? And the shape factor is going to be less than 1, right? And so I want to point something out here, right? R star stays the same, right? So I say it in the rate and the reading, it says it that the critical nuclei size stays the same, but the critical volume is different, right? So here I just have a cap, right? Yes, this cap has the same radius, right? But the volume of this nuclei, the number of atoms I need in this cluster is much smaller, right? Because if I nucleated homogeneously, I would need a whole bubble this size, right? Which in 3D has a lot more atoms in it than just this little cluster, slice, right? So the critical radius stays the same, but the volume of atoms I need in my cluster for nucleation is much, much smaller, right? And so what this translates to, if we look at our free energy curves, is we get a greatly reduced activation barrier for a given undercooling, right? Our critical radius remains the same. Our critical volume is much smaller. And what that translates to is if we consider that we still need this minus 78 kT undercooling, right? It means that our heterogeneous nucleation rate is going to take off at a much, much smaller undercooling than our homogeneous. It still looks like a step function because our Boltzmann statistics are still the same. We still have this exponential probabilities of cluster sizes and all that, but now we're just looking for clusters of a much smaller size, right? And if we're going, we can even assume the same frequency of atomic jumps and all that. So our heterogeneous nucleation rate looks exactly the same as it did for the homogeneous nucleation rate. It just happens much earlier, right? And so if we look at this temperature that we need to nucleate this smaller volume of region, right? We have 0 probability of having a cluster of the critical size for homogeneous nucleation. And this is why almost everything nucleates heterogeneously, right?
So the humps look pretty similar for both of them. It's just that the heterogeneous requires less temperature to get over that hump.
So the hump is for a given undercooling, right? Right. So remember, these free energy curves are at a constant. This free energy curve is at a constant temperature. So for a given undercooling, the humps don't look similar at all, right? You have a much lower activation energy, right? So we can think that the interfacial energy is roughly independent of the temperature, right? That's not a bad approximation to make. The interfacial energy is going to be temperature independent, right? But what goes into the volumetric term, right? The volumetric term incorporates both the undercooling and the surface energy term, right? And so that's by moving this surface energy term, this volume term down, right? That's why this curve ends up having a slightly different shape, right? Because you need a smaller volume of material for the same critical radius, right? And so that's why it just doesn't follow the same exact trajectory over here, right? Because your surface energy is different, and your volumetric, the volume that you need is different as well, right? So does that answer the question, Kevin?
Yes.
Okay. So in reality, we can reduce this volume even more. So everything that we talked about before assumed a flat surface. But in reality, things aren't flat, right? We have all kinds of asperities and cracks and pits, right? And what matters for nucleation is this critical radius. So before, we only nucleated a little cap, right? If we're at the bottom of it, nucleating at the bottom of a crack, now we only have to nucleate this tiny little wedge, and our volume is much lower. So the activation barrier to nucleate here at the bottom of this crack is going to be much smaller than to nucleate even on this flat surface, right? Because we're going to have even less of the high solid liquid interfacial energy and more of the favorable solid mold or solid substrate area. Of course, this is where things get interesting, because we need to make sure that at the top of this crack, we have enough room to grow out, right? If this crack isn't wider than our critical radius, right, we can't grow out of this crack, right? It is essentially the same as another nucleation event that would have to happen, right? We would have to nucleate a new particle here that would then grow over. But if we're narrow at the bottom and wide at the top, we can have nucleation that happens very easily, right? And what about nucleation on a secondary phase particle, right? I said, we can nucleate either on the container, or we can nucleate on dirt or other impurities in our system. Well, in this case, it's not quite as easy, right? Because if we think about nucleating, this is a solid liquid nucleating on a solid particle from a vapor. But we can see that this is the surface energy, the surface area that we need to create by the interface. And it's larger than if this were flat, right? If we drew a straight line flat across here, we can see that we actually have a larger amount of surface energy. So the activation barrier to nucleate on a small spherical particle is going to be larger than by nucleating on a flat surface. But if we pick this inclusion correctly, it can still be a very easy process, right? If this solid liquid surface energy is very low, right? Or in this case, for solidification, our impurity and the substance that we're trying to solidify, if this interfacial energy is really low, it still becomes really easy, right? And in metals, a lot of times we have secondary phase particles, carbides and oxides, that have a much higher melting point than the alloy, right? So that means if we just go above the metal melting temperature, these solid carbides and oxides are still around, and they're going to be very potent sites for heterogeneous nucleation, right? And sometimes secondary phases are added as grain refiners. This is called inoculation, right? So you deliberately add something in there. This happens with aluminum alloys a lot, that stimulate nucleation of grains so that you end up with a very fine grained cast structure instead of a large cast structure, right? And again, this is really critical concepts for the welders, right? Because the you don't have a lot of knobs you can turn for your solidification microstructure, right? You really just have your heat input and what that's going to do to the size of your weld pool and how fast you can cool things down, right? And so understanding what goes into the solidification is really, really important. So the last slide today is just nucleation of melting. And the key idea is that because the surface energy of the solid liquid, right, if we have a solid liquid vapor system, right, the solid vapor interfacial energy is always going to be higher than the solid liquid and the liquid vapor, right? And we can replace substrate and solid and liquid, right? But anyway, so this is generally going to hold. So basically what this says is that there's no penalty for melting. If we're going to create liquid on the surface of a solid, there's no activation barrier that we need to overcome. And in fact, most solids have a thin layer of liquid adsorbed onto the surface. And so we don't need a superheating to melt, but we do need an undercooling to solidify. Okay, so that wraps it up for today. On Wednesday, we're going to talk about growth of pure solids and dendritic growth. And then on Friday, we'll get started with solidification of alloys and mixtures, and when we have chemical segregation that happens during solidification. And then next week, we'll start solid state diffusion. Okay?
Question?
Yeah.
I know, I have a lot of them.
Go ahead.
So the reading, I took a look at them. It said the papers that look kind of interesting are due the 25th, the 2 experiment papers.
Yeah, so they're due Friday, right? I'm just kind of breaking the reading into more smaller reading assignments rather than...
Yeah. The question was, it said on the slide earlier that they're due next week. Was that just a typo or just outdated info?
Oh yeah, because I made these slides last week. Sorry. Yeah, so they are due Friday. Right? So there is a reading quiz on Wednesday on the section 4.1 from the textbook, or 4.2.
4.1 and 4.2.
4.1 and 4.2. Right, so that's due Wednesday, and that's on, what we've been talking about the last couple days. Then Friday, there's the reading of the 2 David Turnbull papers.
I had a quick question as well.
Yeah, go ahead. Who's talking now?
This is Elliot Ogles. I know it just says Ogles. I changed it every single time. It changes right back.
No, that's fine. Because I'm sharing, I can't easily see. Zoom doesn't tell me on the participants window who's talking. So.
Oh, okay.
Well,
my question was
Kevin's voice really well.
Oh, well, my question was more about the mastery questions that you posted. I saw that you changed the grading weights, and mastery is now 20% of our grade. I thought those were more for self-benefit. I didn't think they were graded.
They're not graded. They're graded by it's first off, it's been 20% on the syllabus since before, so that hasn't been a change. But the mastery questions are essentially just, do you complete them, right? Right. So it's just a way of, you can think of it as a small inbuilt grade curve, right? Because they're going to be fairly easy questions that are there just to help you prepare for exams, right? Just to see what the key concepts are that you should be looking at. And they're just sort of automatically graded by Carmen, this third-party plugin that I'm having difficulty working. That's why they're not up yet. But they should be going up today or before the next class, so I can explain them. But essentially, it's just like a Carmen quiz. It'll self-grade, but the grade is essentially just, did you complete it or not? Right? And so you just keep trying the question until you get it right. You have infinite attempts and unlimited time, but they really shouldn't take that long.
Fair enough. Thank you very much.
And so
When are they due?
They will be. There is no due date. It's just you need to get them done before the end of the semester, so that you get 100% in that category.
When will they be posted, or where?
They will be. They'll be posted in each module, and I've almost got it all sorted out, so they will definitely be up before the next class on Wednesday.
I just wanted to confirm that they are not up yet. I was looking for the mastery questions the other day, and I didn't find them. So
no, they're not up yet because getting this software that we have a license for to work has been really difficult, and I've had to Professor Benatar in welding actually took a whole class on how to do this, because it's really like another programming language to get this system to work right. And so I've had to refer to him for help in being able to do this. So you guys are a little bit of a guinea pig on this. So sorry. So we'll see everyone Wednesday. Have a good day. And we'll catch you later.